In this video, we're going to take a closer look at a problem in civil engineering systems analysis, a textbook by Revelle, Whitlach and Wright. The interesting thing about this problem is it has both a steel manufacturer and a local municipality, that is a local government, and the interaction between the two entities, both of whom have their individual systems models, gets really interesting. To help you set this problem up, I want to take you through some of the given information listed here so that you can identify the steel manufacturer and the government's design variables, parameters, constraints. If you remember from an earlier video, the design variables, the parameters, the constraints, and lastly, the objective function were the really important vocabulary words that represent the concepts that we need to understand. So let's see if we can sort out some of this given information. The steel manufacturer has three design variables. We'll call the first one X1, and that's their production. They get to choose how much they want to produce. And typically, steel in a plant like this might be measured in tons or tons per day. So they get to choose how many tons are they going to produce in any given day. If they were going to go out of business, X1 would be 0. And we're going to set a positivity constraint on X1 because they're not in the business of destroying the steel. It doesn't make any sense. And they also need to decide how much pickling waste they're going to treat per day. So we might call that X2, or we might call that Q for a flow pickle, and it's pickling waste, and we're going to call that gallons per day. They also need to decide how much of the process water they're going to call that process they're going to treat, and that's process water also in gallons per day. Now this doesn't say yet how much gets sent to the river. It only says how much gets sent to the treatment plant. So this would be Q pickling and Q process. Right now, there's steel for sale. Right now, the decision variables that we've identified on our diagram are here, here, and here. We don't need to say how much of the pickling waste goes into the river or how much of the process waste goes into the river because of these balance constraints. Once we know how much is going to be sent to the treatment plant, the amount that goes to the river will be calculated by these equality balance constraints. It's going to be whatever came out here minus what's treated, that's what goes to the river. So these are the design variables for the steel manufacturer. They have some other things, some other parameters. When they sell steel out to the market, right now they sell it at $25 a ton. And you can imagine that that parameter is going to show up in their objective function. The amount of pickling waste generated. So that's going to be Q pickle, but not the same Q pickle that goes here. That's going to be the amount of pickling waste is going to be 100 gallons per ton of steel. So that is Q pickle that goes to the river. I hope this makes sense to you. The design variable is the flow of pickling waste that goes to the wastewater treatment plant. 100 gallons per ton pickling waste, this is for pickling waste, times the number of tons produced, minus the amount of pickling waste that goes to the treatment plant, that's what winds up in the river. So what I've created here is this balance constraint, and it's equality because there's no storage at this node. What comes out is 100 xi. What goes to the treatment plant, it must equal what goes to the treatment plant and what goes into the river. And we can do a similar thing for the process waste. Here it's 1,000 gallons minus the process that is treated, and that equals the process waste that goes to the river. Terrific. We're working our way through the parameters. There are going to be more costs. The cost of treating pickling waste, 2 cents per 1,000 gallons. Keep in mind that these units are going all over the place. We got gallons, gallons per day, we got 2 cents per gallon, and you're going to have to be careful. And gallons per ton, you're going to have to be careful about how you treat your units. Also, it has an interesting complication. For the pickling waste, there's a pre-treatment cost and a treatment cost. So we really need to add these two together, this being the pre-treatment cost and the treatment cost being 10 cents per 1,000 gallons. Now we have a sense of the total cost of treating pickling waste. Now we got to move on to the process waste. The treatment cost of the process waste, because it doesn't require pre-treatment, is only this 10 cents. This is for pickle, and this is for pickle and process. So you got to sort out in the cost function what the cost of treating the pickling waste is. It's more expensive, and what the cost of just treating the process water is. Those are some of the parameters. We also have, in the simplest version of the problem, tax costs. If the government taxes are known, then there's the tax of 15 cents per 1,000 gallons that's paid for, this is for river discharge, on the pickling waste. And for process waste, this tax shows up as 5 cents. That's because the pickling waste is stronger, it's more concentrated than the process waste. So the government might set a higher level of the tax. Now we have a couple of constraints. The treatment capacity in the wastewater treatment plant, QW pickle plus QW process, is another special kind of process constraint. It has to be less than or equal to 50 million gallons a day. There's also a pre-treatment constraint that's just on the pickle, and that's 2 million, again, if I can get this right, 2 million gallons per day. We're sorting our way through everything that we have, and there's one more set of constraints, and that's the limit on the pickling waste that can be discharged directly into the city sewers without treatment. It winds up in the river. Those two are going to be represented here, and they have to be less than or equal to, for pickling, 500,000 gallons a day, and for processed water, 10 million gallons a day. Now we've sorted through each one of these given pieces of information. These are the design variables. These costs and prices, they're parameters that show up in the objective function. These treatment capacities, constraints that limit the design variables. The taxes are going to show up from the steel manufacturer's perspective as parameters again that go into the objective function. And then these limits are additional constraints. I didn't mention the treatment efficiency. I'm going to let you figure that out for yourself. And then we're going to get to what's really interesting about the problem. You're going to need that treatment efficiency because the more efficient the plant is, the less pollution goes into the river. But it isn't necessarily, we don't have to set it up so that the problem is sensitive to the treatment efficiency. For now, all you need to know is that there's still some sewage that winds up in the river. That is, they still need to pay for what comes out of the wastewater treatment plant and is discharged to the city. They just pay a lot less because it's been treated. All right, what about the government? In the simplest version of the problem, the steel manufacturer accepts these taxes as parameters that fit into their systems model. But in the more complex, in the multi-objective problem, where we want to explore the empathetic capacity of the government for the steel manufacturer, these appear as parameters to the steel manufacturer, but they are design variables to the government. In this two-player game, the government would first choose their taxes, and then the steel manufacturer would re-optimize their model to respond to whatever the changing taxes are. It gets really interesting when we start doing a sensitivity analysis. I'll show you that in the next video.